Welcome to the Deep Dive. This is where we take material you've chosen and, well, we extract the key insights, giving you that shortcut to being genuinely well-informed. Today, we're tackling a really significant piece of research. It's focused on a vital question, the future of our energy systems.
Exactly. We're diving into the study titled Energy System Transition Pathways to Meet the Global Electricity Demand for Ambitious Climate Targets and Cost Competitiveness. And you, our listener, you flagged this important work. You're clearly interested in understanding, how we can effectively decarbonize the electricity sector.
Without breaking the bank, right?
Precisely. Cost effectiveness is key.
Absolutely. And, well, you'd be hard-pressed to find a more critical challenge these days. The need to address climate change is urgent, and the energy sector.
Yeah.
It's a major source of emissions, so it's right there in the spotlight.
Yeah.
Okay, let's get into this detailed analysis then.
Yeah.
What's the sort of overarching picture this study paints?
Well, this study gives us a pretty broad analysis. It compares 9 different potential pathways for the global electricity sector, how it might transition to a more sustainable future.
9 pathways.
Yeah, and it looks at the period from 2015 all the way out to 2050. It breaks things down into 5-year chunks across 9 major global regions.
9 pathways, 9 regions until 2050. That's a huge scope. What makes the comparisons in this particular study so robust?
Well, what's especially insightful, I think, is that all 9 of these future scenarios, they were modeled using the exact same underlying technical and financial assumptions.
Okay.
So this consistent framework, it allows for a much more direct, much more meaningful comparison of their projected outcomes. It's like, setting up a level playing field for all these different energy futures.
That makes perfect sense. So you've got this level playing field. What were the main criteria the study used to actually compare these different pathways?
It mainly focused on 5 key areas. First, the projected costs of generating electricity. Second, the variety of energy sources used, the energy mix.
Right, diversity.
Then third, the system's ability to adapt to fluctuating supply and demand, what they call flexibility. Fourth is energy security, obviously important. And finally, the dynamics, how the transition actually unfolds over time.
Okay, cost, diversity, flexibility, security, transition dynamics. Got it.
And the study also emphasizes that the electricity sector is probably at the forefront of decarbonization compared to other sectors like transport or industry.
Which makes sense, right? It's maybe easier to tackle first.
Potentially, yeah, which justifies the specific focus here.
Right. Electricity touches so much of modern life. Cleaning up its production has this huge cascading effect. Now, these 9 different visions for the future, where did they actually come from? Who developed them?
Okay, so the 9 scenarios come from 3 distinct and, pretty well-respected sources in energy system modeling. First up, we have the International Energy Agency, the IEA. They offer the stated policy scenario, STEP S, which basically reflects current government energy policies around the world. Kind of the business as usual plus current plans view.
Right, what's already on the book.
Exactly. And they also present the Sustainable Development Scenario, or SDS. That's a more ambitious pathway aiming for net zero emissions by 2070.
Net zero by 2070. That's still quite a ways off, but a significant step. Yeah. Now, I noticed the study mentioned the IEA's net zero emissions by 2050 scenario wasn't included in this comparison. Why was that left out?
Correct. Basically, at the time the specific study was conducted, the IEA hadn't yet released the detailed regional data needed for their NZD 2050 scenario.
The granularity wasn't there.
Exactly. And since this study analyzes things across 9 specific global regions, that lack of regional detail made it impossible to incorporate it into their comparative modeling framework. It's just a practical limitation. And it's worth noting, the IEA's scenarios, they often envision a continued role for fossil fuels, maybe with carbon capture and storage, CCS, and also nuclear power in some of their projections.
Right, keeping those options open. Okay, that's the IEA perspective. Who else contributed scenarios to this study?
The second set comes from a collaboration. It's the University of Technology Sydney and the German Aerospace Center, DLR. They're often referred to together as TESC DLR.
TESC DLR, got it.
They developed 2 scenarios. A 2°C scenario and a 1.5°C scenario, both aiming for, deep decarbonization by mid-century.
And what's their core philosophy here? How does the TESC DLR approach, as shown in this study, differ?
Their approach is described as heuristic, multidimensional, and with a really strong emphasis on diversifying energy sources.
Heuristic, meaning?
Meaning they're using maybe a broader, more practical set of considerations, not just pure mathematical cost optimization. They also specifically aim to phase out nuclear power entirely.
Okay, no nuclear.
And they want to avoid large-scale hydropower and CCS technologies. Plus, they limit the use of even sustainable biomass. So it's quite a different vision. If the IEA keeps several options on the table, TESC DLR in this study takes a more decisive stance against certain technologies.
That is a clear contrast, definitely. What about the final set of scenarios analyzed in this study?
The last group comes from LUT University. They developed what they call the Best Policy Scenario, or BPS, and then several variations on that theme, 5 scenarios in total from them.
5 from LUT. Okay.
Yeah, you have BPS NWF, BPS WF, and then these more accelerated transition timelines. BPS plus 2040, BPS plus 2035, and the most rapid one, BPS plus 2030.
Best policy.
Yeah.
That sounds pretty optimistic. What's the defining characteristic of these LUT scenarios as outlined in this study?
The key feature really is their focus on cost optimization. Their main goal is achieving zero CO2 emissions with a 100% renewable energy system.
100% renewables.
Yes, and those different plus scenarios just explore hitting those goals by different target years, ranging from as early as 2030 all the way up to 2050.
Wow, 100% renewables by 2030? That is incredibly ambitious.
It is a very fast track.
So we've got these 3 distinct sets of scenarios in energy system transition pathways to meet the global electricity demand for ambitious climate targets and cost competitiveness, each with its own logic, its own assumptions. When we look at what they project for actual energy capacity and generation, what were some of the major findings?
Well, what's really striking in the LUT-BPS scenarios presented in this study is the projected dominance of solar photovoltaic PV by 2050.
Solar really takes over.
Massively. They see solar PV becoming the #1 source for both installed capacity and actual electricity produced. Wind power follows pretty closely behind.
Just how much solar are we talking about?
The study anticipates a huge expansion. The range is something like 19.7 to 26.3 terawatts of solar PV capacity by 2050, depending on which specific LUT scenario you look at.
Terawatts. That's an enormous amount of solar. Do the other scenarios in this study also predict such a big role for solar?
The TESC DLR scenarios and energy system transition pathways to meet the global electricity demand for ambitious climate targets and cost competitiveness also project a substantial role for both solar PV and wind, definitely. But remember their focus on diversity.
Right.
So they include more significant contributions from other renewables like concentrating solar power, CSP, geothermal energy, even ocean energy.
Okay, a broader mix.
Exactly. And then you contrast that with the IEA scenarios, particularly the STEP-S pathway. They anticipate continued growth in nuclear power and even in fossil fuel capacity, both with and without CCS.
So IEA STEPS keeps fossils in the mix significantly.
Yeah. Now, the IEA's SDS scenario, the more ambitious one, it does incorporate a greater share of renewables as you move towards 2050, but it still maintains a, let's say, considerable reliance on non-renewable sources compared to LUT or TESC DLR.
Right.
So you see a real divergence in the long-term energy mix envisioned by these different groups. It's quite stark.
A very different picture indeed. LUT in this study heavily focused on solar and wind. TESC DLR wanting a broader spectrum of renewables, and the IEA seeing a continuing role for more, let's call them conventional, power sources. Okay, let's talk economics. Which of these pathways outlined in energy system transition pathways to meet the global electricity demand for ambitious climate targets and cost competitiveness actually looks the most cost-effective?
Well, the good news is, across most of the ambitious decarbonization scenarios analyzed in this study, there's a projected decrease in the global average levelized cost of electricity, the LCOE, by 2050.
Costs go down even with the transition.
In most ambitious scenarios, yes.
Yeah.
And when you compare the estimated LCOE ranges in 2050, the LUT-BPS scenarios, they generally appear to be the most cost-competitive pathways.
How much lower are we talking?
Their LCOE estimates range from about 45.2 to 49.7 euros per megawatt hour. The TESC DLR scenarios come in slightly higher, around 53.9 to 54.1 euro milli-farad, and the IEA scenarios show a broader range from 59.2 up to 69.5 euro milli-OHE.
Okay, so quite a difference there. It's interesting that even the IEA's STEPS-S scenario, the one relying heavily on fossil fuels, shows some cost reduction over time.
It does show a gradual reduction, yeah.
But it sounds like this study suggests that a 100% renewable energy system might actually be the most economical way to get to zero emissions in electricity. That sort of flips the traditional argument about the high cost of going green, doesn't it?
Precisely. That's a key takeaway. And when you look at the total cumulative costs of these different pathways over the whole period,
Right, the total bill.
this study indicates that the LUT scenarios are projected to be significantly lower overall.
Lower total costs.
Yes. The IEA Steps S scenario, which maybe requires the least upfront investment,
Hmm.
it actually becomes the most expensive in terms of LCOE by 2050.
Why is that?
It's largely attributed to the continued dependence on fossil fuels and, the associated fuel costs and potential carbon pricing down the line. So sometimes the path that looks cheapest initially,
Ends up costing more in the long run.
exactly, it can end up being the most expensive.
That's a really important point to consider. Okay, now, with such a massive influx of renewable energy, especially from variable sources like solar and wind, how do these scenarios in energy system transition pathways to meet the global electricity demand for ambitious climate targets and cost competitiveness, tackle that crucial issue of system flexibility? How do you guarantee power when the sun isn't shining or the wind isn't blowing?
Yeah, that's fundamental. And this study highlights the absolutely critical role of energy storage in any scenario with high renewable penetration. You just can't do it without storage.
What kind of storage?
They considered a range of technologies, batteries, obviously, but also pumped hydroelectric storage, hydrogen storage, even thermal energy storage. Think of it like, well, if solar and wind are like these intermittent bursts of energy,
Right.
storage acts as the buffer. It captures that energy so you can use it whenever it's needed, smoothing things out.
And what did this study find about the amount of storage needed across these different pathways? Does it vary much?
It does. The LUT BPS plus scenarios, the ones with the really fast transitions to 100% renewables.
The 2030, 2035 ones?
Exactly. They show an earlier and a much more significant need for substantial energy storage capacity. Makes sense, right? The faster you go, the more storage you need sooner.
Okay.
On the other hand, the IEA scenarios rely less heavily on energy storage. Why? Because they still have these dispatchable power sources like fossil fuel plants, some with CCS, and nuclear power. Those can adjust their output more easily to meet demand.
So they need less of that storage buffer.
In theory. Though, interestingly, the study points out that the storage capacities they modeled for the IEA and TESC DLR scenarios sometimes differ from what was in the original studies those scenarios came from.
How so?
It potentially indicates that maybe even greater storage might be required when you analyze these scenarios with more granular, like hour-by-hour models, as this study did. The need might be even higher than first thought.
Interesting nuance. So the more renewables, the more absolutely essential storage becomes for grid stability. Now, let's get to the core goal, cutting CO2 emissions. How do these different pathways in this study stack up environmentally?
This is where you see the most dramatic distinctions, really, between the scenarios in energy system transition pathways to meet the global electricity demand for ambitious climate targets and cost competitiveness. It's night and day in some cases.
How so?
The LET scenarios project very rapid, very deep reductions in CO2 emissions. They're aiming for zero emissions in the electricity sector by 2050, or in those pluses scenarios, even sooner.
Okay, zero emissions target.
The TESC DLR scenarios also show a consistent downward trend in emissions, heading towards those 1.5 or 2 degree targets.
Those are significant reductions.
Yes, but then you look at the IEA STEP scenario, it shows only a modest reduction in emissions over the entire time frame to 2050.
Just a slight dip.
Relatively slight, yes, compared to the others. And notably, the LUT BPS plus 2030 pathway, that super fast one, it's identified in this study as having the lowest cumulative CO2 emissions by 2050 across all the scenarios they analyzed. So fastest transition equals least total pollution.
That really underscores the varying levels of ambition baked into these different visions, doesn't it? Some are aiming for a radical transformation, others much more incremental change.
Absolutely.
This brings up an interesting point you touched on earlier. This study mentions a potential trade-off between having a really diverse range of energy technologies versus achieving the absolute lowest, most optimized cost. Can you break that down a bit more?
Sure. So the TESC DLR scenarios, and maybe the IEA scenarios to some extent, they prioritize having a more diverse mix of technologies.
Like not putting all eggs in one basket.
Exactly. The thinking is that greater diversity could enhance energy security and resilience, makes the system less vulnerable if there's a problem with, say, one specific technology or fuel source.
Makes intuitive sense.
But The cost optimization approach used in the LUT scenarios, as highlighted in this study, suggests that the most cost-effective route to zero emissions in electricity by 2050 seems to be through this dominant reliance on solar PV and wind, potentially with less emphasis on some other, maybe currently more expensive, renewable sources.
So it's cost versus resilience,
Yeah.
potentially, or cost versus diversity?
It's sort of a question of whether the potential benefits of that broader energy portfolio outweigh the potential cost savings you get from a more focused, optimized approach, leaning heavily on the cheapest options, which right now look like solar and wind.
So it's a bit like deciding whether to invest in just a few really high-performing stocks or diversify your portfolio for potentially lower but maybe more stable returns.
That's not a bad analogy, yeah.
And this study also touches on some of the downsides or risks associated with sticking with fossil fuels and nuclear power, doesn't it?
Yes, it does implicitly. Continued reliance on fossil fuels carries obviously significant environmental consequences, but also the increasing financial risk of stranded assets.
Assets becoming worthless.
Investments in fossil fuel infrastructure that lose value rapidly as the world transitions to cleaner energy. And nuclear power, while it is low carbon during operation, faces its own challenges, high upfront costs, ongoing safety concerns, and the whole long-term issue of radioactive waste disposal.
Right, those haven't gone away. On the flip side, the LUT scenarios in this study lean so heavily on solar PV and wind. Are these technologies really mature enough, and can they be scaled up fast enough to handle such a massive energy transition? That 2030 target seems intense.
Yeah, it's a fair question. The study points to the increasing maturity, the proven scalability, and especially the rapidly declining costs of solar PV and wind power. The ambitious targets in the LUT scenarios reflect this confidence.
But is the scale-up feasible? That manufacturing challenge alone sounds huge.
Well, the study suggests that while the sheer scale of manufacturing and deployment needed, especially for those very rapid transitions like the 2031, is considerable, it's potentially achievable. Ambitious, yes, but maybe not impossible. Meanwhile, other renewable sources like hydropower, bioenergy, geothermal, ocean power, they face various limitations, perhaps in terms of global scalability, geographic constraints, or overall sustainability concerns.
So solar and wind are seen as having fewer constraints globally.
In terms of rapid, large-scale deployment potential and cost-effectiveness, yes, that seems to be the finding here. And of course, technologies like CCS and nuclear power come with their own set of technological hurdles and deployment uncertainties we just mentioned.
And storage is the key enabler.
Absolutely. Battery storage in particular is identified in the study as just crucial for enabling these high levels of solar and wind penetration. It makes the whole system work.
Of course, any model looking decades into the future involves uncertainty. This study itself acknowledges some limitations, right? What are the key ones we should keep in mind when thinking about these findings?
Definitely. It's crucial to remember that long-term energy system modeling is inherently uncertain. Predicting future technology costs, for example, is always tricky.
Did they test for that?
They did. This study performed a sensitivity analysis using the cost assumptions from the TESC DLR scenarios, which were maybe a bit different. And while that did have some impact on the projected LCOE and overall system costs, the fundamental trends like renewables being lowest cost for decarbonization remained largely consistent.
Okay, so the core findings held up. What else?
Another simplification in the study is using just 9 major global regions that might not fully capture all the specific circumstances and variations within individual countries or smaller areas. Reality is always more complex.
Sure, averages can hide local differences.
Exactly. Furthermore, the study mainly focuses on the electricity sector. It doesn't deeply explore the potential impacts of, say, much greater grid interconnections between these regions, or the integration of electricity with other sectors like heating and transport, what's called sector coupling. Those could change the picture.
Right, looking beyond just electricity generation.
And finally, those more ambitious scenarios, especially the LUT ones, they often implicitly assume a significant degree of international cooperation and support of government policies are actually put in place to make these rapid transformations happen, which is, a big if.
A very big if indeed. Political will is key. So while energy system transition pathways to meet the global electricity demand for ambitious climate targets and cost competitiveness gives us a ton of valuable insights, it's still a model of a complex future. The actual path could look different.
Of course, models are tools, not crystal balls.
But to sum it all up then, what's the core message, the main takeaway that emerges from this deep dive into this study?
I think the central message of Energy System Transition Pathways to Meet the Global Electricity Demand for Ambitious Climate Targets and Cost Competitiveness is pretty clear. It indicates that a rapid, large-scale shift towards renewable energy sources, particularly solar PV and wind, coupled with the widespread deployment of energy storage, that appears to be not only the most effective strategy for decarbonizing electricity, but also the most economically sound option in the long term.
That's a really powerful conclusion. So hitting zero CO2 in electricity isn't just about the environment. According to this study, it could actually be the most financially prudent path forward.
That's precisely what the findings of Energy System Transition Pathways to Meet the Global Electricity Demand for Ambitious Climate Targets and Cost Competitiveness strongly suggest, yes. Transitioning to a fully renewable electricity system, it's presented here not just as a possibility, but potentially a more economical reality than sticking with current policies heavily reliant on fossil fuels.
And even though there are these different approaches and priorities shown in the scenarios of this study, cost optimization versus energy diversity, the overall direction of travel towards renewables seems pretty undeniable in the ambitious pathways.
Yes. As highlighted quite clearly in Energy System Transition Pathways to Meet the Global Electricity Demand for Ambitious Climate Targets and Cost Competitiveness, while various pathways exist, the scenarios aiming for deep decarbonization through rapid renewable adoption consistently outperform the business-as-usual type scenario, both on cost and obviously on environmental impact.
This has been a genuinely insightful deep dive into energy system transition pathways to meet the global electricity demand for ambitious climate targets and cost competitiveness. It certainly gives us, and you, the listener, a lot to think about regarding the future of our energy systems.
Indeed it does. And maybe it prompts a crucial question for you, our listener, to mull over. Drawing on these findings from Energy System Transition Pathways to Meet the Global Electricity Demand for Ambitious Climate Targets and Cost Competitiveness, what do you see as the biggest hurdles? Are they technological, political, societal, to really accelerating this transition to a fully renewable electricity system where you are? And what further questions does this kind of detailed analysis raise for you about this incredibly complex and critical topic of our future energy landscape?